Okay, welcome to everybody. I'm very happy to be connected with, I hope, many people to follow this seminar, the seminar of this afternoon about this very important topic, which is artificial intelligence and methodology. I will be very short because the real greeting will be given by the first speaker, which is Professor Francesco Ubertini. And Professor Ubertini is a part to be the president of the IFAB Foundation, which is one of the two co-organizers of this seminar. Has been up to very recently the rector of our very old and famous University of Bologna. So it's a pleasure, Professor. It's up to you.
Thank you. Good afternoon, everyone. I'm very pleased to open this webinar co-organized by IFAB, the International Foundation Big Data and Artificial Intelligence for Human Development. I'm honored to chair, and ECMWF. Let me spend just a few words about IFAB. It was founded to create a bridge between research and industry in a very crucial area, big data and artificial intelligence, and to support the activities and the development of the big data technopole in Bologna, where an amazing computing infrastructure is concentrated. Let me mention the two largest infrastructure, the ECMWF data center on one side and the Leonardo supercomputer that is going to be activated next year, together with advanced research institutions operating in different sectors. Digital transformation is generating an explosion in the production of data, which is perhaps the most precious raw material of this historical phase. And the IFAB Foundation works to create public-private synergies and partnerships focusing on projects of common interest where big data and artificial intelligence find application in the great challenges of our present, such as climate change, sustainable mobility, the management of health emergencies, and the new frontiers of care, and so on. The objective is twofold: to support the European production system on one side and to make a fundamental contribution to the transition towards a sustainable society. But let's come to our webinar, and we are going to present an important research project funded by IFAB and carried out by ECMWF. Let me thank first Sanzio Bassini, the IFAB Technical Scientific Coordinator, Florence Rabier, Director of ECMWF and member of our International Scientific Board. Let me thank Tiziana Paccagnella, member of our advisory board, expert in climatology, who has organized the webinar, the entire ECMWF research team for the important results achieved that we are going to listen in a while. And I would like also to thank all of you, the public, for their participation. I was told that over 300 people register from all over Europe. So thank you to everybody. I really hope that this initiative will be followed by many others, also given the great interest that has been expressed. So I leave the floor to Tiziana. Good webinar and good work to everyone.
Okay. Thank you, Professor Ubertini. And now I will give the word, in a certain sense, a very Italian way to say, and to Sanzio Bassini, which is the director of supercomputing application and innovation at the Cineca Computer Center. And and he will talk also about this, the foundations.
Thank you very much, Tiziana. Thank you very much, Professor Ubertini and all. It's a real pleasure to introduce this webinar and the two lectures that will follow after the introduction, just because I think that the subjects are really very much important. The circumstances that lead to the opportunity for addressing these actions have been, as it often happen, circumstances that has to do with the interaction and common sharing of the vision with respect of what are extreme challenges and what are also the way that we do need for proceeding step by step in a context which is absolutely very much challenging in our time. I'm talking about the compilations, the combination of different methodology, the method of the numerical simulations, and the method of integration of data processing based on machine learning and artificial intelligence approach, that it would lead to what it could be a real, let's say, effectiveness with respect of what could be the opportunity for services to the different agencies and the different level of decisions that it would lead to taking opportunity strategy to face what would be one of the major challenges of our time, the climate change, and the impact with respect of the life on the planet, from the biodiversity to the what could be the opportunity of maintaining our level of development and our level of welfare. So from the point of view, the topic is really very much important in general speaking. The opportunity for combining numerical simulations and practice based on artificial intelligence in a so challenging domain as the climate and the climate change impact will lead to the possibility, in combination with what it could be the exascale computational power that will be available in the next coming months and years, to have evidence of what it could be the impact in terms of the taken decision with respect of the different actions that could have been taken in order to address what it could be the solutions for the mitigation at the very beginning, and then the solutions related to the climate change issues. That in general speaking, the specific matter do represent a leading scientific case towards exascale that has been included into the different documentations that has to do with the high performance computing infrastructures at the European level, either the current that will be based on beta scale and pre-exascale systems, either which could be the follow-up based on full exascale and the full post-exascale. From this point of view, the two different seminars, lecturers that we are going to attend and to assist would, on one side, combine what it would be the error mitigations and solutions, that it's a very important practice that it would lead to the improvement of the numerical simulations, and so the effectiveness of what will be the forecast in providing decision support that be more and more effective. That is the first lecturers. The second lecturers would be the combinations of approaching based on complex systems that it's really very much appropriate also in timing, just to follow what would be the awarding of the Nobel Prize to one of the most significant scientists of our times in this context, Professor Hasselmann in Germany, and our Professor Parisi in Italy, that it would be our mentors of all tests somehow share and chance to study physics. Both would be extremely important steps with respect of what would be the capability to facing the issues represented by these two specific problems in a more complex vision that it would address what could be the combinations of the numerical method and the machine learning and artificial intelligence approach. So really very much interesting and really very much important, I would say. I would definitely thanks very much ECMWF and Florence Rabier that would address and define what would be the opportunity for sharing this experience, and also Tiziana that has the merit to rationalizing from the point of view what would be the IFAB action, what been the matter of the subject. And I think since now that we should have to address what would be persistencies in this context. In representatives of Professor Cacciamani that for personal reasons and small illness it cannot be today with us. I would think that combining the joining effort between our institutions, including CINECA, the IFA foundations, but also ECMWF and the new Italiameteo agency, in the context of development what will be the process addressed and lead by the two topics and the many others that will come, would represent absolutely a commitment challenge on our side that I would hope that it would define opportunity for further collaborations and further opportunity. There have been also the opportunity, generally speaking, to include those kind of subjects in multilateral collaborations, that it would include also other institutions in Italy and other institutions at the European level, that it would progress in this context in a sort of general shared vision that it would lead to facing and maybe solving one of the big issues of our time, which is represented by the climate change and the impact that we do have to face in the next coming years. So thank you very much, and really pleased and would thank the two next speakers, Peter and Warwick, that would made a very good job. I saw their abstract, and I would think that their lecture would be very much interesting. Thanks very much.
Thank you, Sanzio. So we proceed with this introductory part, and the next speaker is Florence Rabier. And Florence, in addition to being the director of ECMWF, she is also a leading scientist in numerical weather prediction and data simulation. So, Florence.
Thank you very much, Tiziana. And really, it's a pleasure to have been invited to give a small introduction to this event. So, as you've heard, IFAB is very active in promoting artificial intelligence for public good and human development. And this seminar is really an example of how it can help progressing this activity in the field of weather and climate. And this is where the link with ECMWF is. So for those of you who might not really know us, ECMWF is the European Centre for Medium Range Weather Forecasts. We are an intergovernmental organization created in 1975 to advance weather forecasts, to push the limits of weather forecasting, make it useful up to 10 days ahead. So this is our role, together with the 34 countries supporting us in Europe, advancing science in numerical weather prediction to make always more accurate weather forecasts and making them useful further in the future. We also operate the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service on behalf of the EU, and we run flood and fire danger forecasts for the Copernicus Emergency Management Service. In this context, I would like to note that we are shortly going to sign a memorandum of understanding on the Copernicus Mirror program in Italy. So ECMWF is now distributed over 3 locations. Our headquarters in Reading, offices in Bonn, and the data center in Bologna, as you've heard. This new data center has been inaugurated in September. It is brand new, state-of-the-art building, and it just received the highest certification, the Platinum certification in sustainability. It will host our operational supercomputer and our large archive. And as you heard, it will be next door to where Cineca is, with also the Leonardo supercomputer from the EuroHPC joint undertaking. As Sanzio mentioned, I'm sure it will open avenues for collaboration between ECMWF and Cineca, but also Italiameteo and IFAB, as computing and AI machine learning are key to the future success of Earth system monitoring and prediction. It's very important for society to have accurate forecasts of weather, and in particular of extreme events. And using AI and ML is one of the components that will help achieve this. As will be discussed with Peter Duben later, machine learning can be used in a huge varieties of ways in our system. Traditionally, our modeling has been based on the laws of physics of the Earth system, which is the atmosphere, the ocean, the land. And then we use observations which have a value in prediction to document what the weather is like today in order to then predict the weather in the future. But they're also at the heart of the reanalysis process, which is fundamental for documenting climate change. We then go back decades ago and we reanalyze all the data to show what the climate was by combining these past observations with modeling. Observations are also used for verifying our forecasts and for refining them, adapting the output of our numerical model based on the local observation. And this is what the talk today is about. I would like now to say a few words about a new European Union initiative where these topics are going to be at the center of the activity, and for which we are going to partner with the European Space Agency, ESA, and EUMETSAT. This is the Destination Earth Initiative, or DESTINY. It's one of the initiatives identified by the communication, A European Strategy for Data, building on the Green Deal data space. In fact, the European Green Deal goes hand in hand with the digital transition, and this culminates in this initiative, which will combine the EU's investment and activities in AI, supercomputing, cloud computing, and high-speed connectivity networks, and Earth observations, while bringing together European scientific excellence and also, very importantly, industrial excellence. So Destination Earth aims to develop a very high-precision digital twin, digital model of the Earth, to anticipate, monitor, better understand, and react in time to the climate change challenges that are ahead of us. So this is what we call a digital twin of the Earth, which is a sort of living digital replica of the Earth that will give us new knowledge so that we can protect the future of our planet. So you have the real world, the real physical world. So as I said, atmosphere, ocean, land, vegetation, glaciers, polar caps. You also have observations of this physical world coming from satellites, but also measurements on the ground and data from Internet of Things as well. And then you have these dynamic models of the Earth system based on all our scientific knowledge of the evolution of the planet, the physics basically. And the digital twin will be driven by this advanced modeling and by AI, and will be fed by this continuous flow of observations from the physical world. So it will combine all this information to give some insights about how our planet works, to revisit the past, to understand the present, and to reveal our future. So the first very important aspect is that this digital twin of planet Earth will have unprecedented precision, providing forecasts of floods, drought, and fires from days to years in advance. Improving the resolution will then give new insights on days and entire decades, providing huge benefits to many sectors. This will, of course, require large computing resources, and we expect that the EuroHPC Leonardo computer in Bologna will play a key role in providing part of these resources. A second important aspect, the model will also incorporate real-time data about atmospheric pollution, crop growth, forest fires, and other phenomena known to affect weather and climate. It will fold in also data about society, such as energy use, traffic patterns, human movements. And finally, importantly, in particular for this seminar, it will make full use of AI and sophisticated data analytics, and will allow the users to interact with the data from the digital twin. So you can think of a digital platform which will provide extreme scale modeling, simulation, and prediction capabilities to its users, while allowing them to customize the platform, integrate new data, their own data, and develop their own applications. So in conclusion, AI and machine learning are going to be even more relevant in the future for weather forecasting and climate monitoring. So you will now see an example on how this has already been progressed thanks to IFAB. And there will be many more opportunities in the future, also with Cineca, academia, and the industry. And with this, I will hand back to Tiziana. Thank you.
Thank you, Florence. So now I think that it's time that I do my presentation. I'm the first trying to use this internet clicker, which is a little bit tricky, but I hope I succeed. Okay. Thank you. I'm here now. I activated the clicker. So, as has been already mentioned before by Sanzio Bassini, in a certain sense, I'm speaking on behalf of Carlo Cacciamani, who has been recently nominated director of the new agency, national agency, meteorological agency, which is called Italiameteo. So, the agency actually has been established almost 3 years ago, in December 2017, and the agency has been put directly in the law that will be located in Bologna. And at the same time, when the agency was established, also the steering committee, in Italian is Comitato di Indirizzo for Meteorology and Climatology, was also established. And the duty of this committee is to oversee the strategy of the agency. And during these 3 years, before the nomination of Carlo Cacciamani as director of Italiameteo, the steering committee has worked a lot, and it is formed by 13 members, and 6 are representing regional administrations or provinces, and 6 are representing national body ministers. And the coordinator, the 13 member, is appointed by the National Civil Protection Department, and Carlo Cacciamani was the coordinator during this 3 years. And it's very important it's something that in the meteorological community is well known in Europe, but I want just to stress that until that moment, Italy never had a civil national meteorological service. So many of the duty of a national service have been carried out by the meteorological service of the Italian Air Force. And this, since of course they couldn't cover all the field related to meteorology, use of meteorology and meteorological application. This situation has led during the last 30 years to the birth of a regional meteorological service, and to the fact that in other bodies, both at regional and national level, the scientists start to develop operational system to produce operational services. So, which is the main action of the steering committee? What we did I'm one of the 13 members of the steering committee, and what we did during this year was, of course, a lot of organization things, but the two main issue was to define and to write the statute of Italiameteo, and also to work to give all our support to the definition also of the regulation of the agency. And a very important work we did was to try to make a comprehensive reconnaissance of the assets and resources available in Italy, because as I said before, many services are spread around, and there are a lot of local administration services, and so it was very important to try to understand which is our starting point to build on these experiences and on these assets to proceed in a positive way with Italiameteo. And of course, Italiameteo will cover all the activities that a national service carry on. So, of course, all the activities related to meteorology and climatology should be coordinated by Italiameteo. There are a lot of work trying to define the good agreements between this new agency and the public administration that we have called weather entities, Entimeteo, which are already existent and that are already producing services and that developed a lot of knowledge during this year. And so it's very important to be able to establish very good links with them and to go on working together. This new agency will be structured in 4 departments: one operation and communications, the other one is infrastructures, the other research and development and training, and of course the last one is administration and human resources. And the other important role that will be covered by Italiameteo is the representation of Italy in the international, very important international organization. Of course, ECMWF is the first one, and then UNSOT and the World Meteorological Organization. And furthermore, and very important, it will be an official reference for the Italian data. This could seem a very trivial things, but it's not this the case, because since the meteorological network are managed by also by regional administrations. So the possibility to put all this data together is very important, because this will allow for a much better coordination, both at operational and scientific level. So, of course, I think one of the first action by Italiameteo and Italiameteo will be to write this kind of contract or this cooperation document between Italiameteo and these weather entities to be sure that all the system will be able to work together in a fruitful way. In the next slide, I made a list the present list of the current list of these entities, weather entities, which is attached to the regulation. And of course, this is a list that could change during the time, and probably every couple of years it will be updated. And I've put this sort of here to just to try to mean that Italiameteo will drive a kind of very complex system that and because this system works, all this small part should be good and work together. So this is a kind of very picture of very simple picture about the topic of the data. So Italiameteo will receive data from all the international bodies and cooperation, because of course there is a lot of cooperation on international level, because of course meteorology is a worldwide topic, and so it's very important that we have a good monitoring of the Earth altogether. And then the Italian agency Italiameteo will send this data around and will collect the data from the other weather entities in Italy. So I want just to conclude saying that another very important issue for Italiameteo is to be able to establish a strong link with academia and research. And of course, without a national meteorological service, this is in the past was not very efficient, this process. But now there is really the will to cooperate and to work with a strong relationship, because it's clear that it is impossible to increase in our knowledge in meteorology, our scientific knowledge in meteorology, and to improve our operational activities and product if we don't have a good transfer between research and operation. And we need a very strong link with academia, because we need good scientists that should have a good background to contribute to the system. The last remark is about the technological pole. Of course, this has been mentioned, and this is a very positive fact for Italiameteo, because Italiameteo will be very near to a place in which there is a lot of technology and science that are very useful for to start and to develop something very important. And in particular, of course, there is a possibility to cooperate with IFAB, with the ECMWF, and with all the environment, not only from Bologna, of course, because now we don't have the problem that today is an example that we can easily speak even without being very near each other. And in the field of supercomputing, artificial intelligence, and the possibility to manage big data. And meteorology is a clear example of big data. And so the next speakers will be Peter Duben and Fenwick Cooper, and they will talk about their experience, and they will give a very good example of what we mean with application of artificial intelligence in meteorology. So the first speaker, if I'm correct, is Peter Duben. Peter Duben is a scientist at ECMWF. He's a specialist of artificial intelligence, but is also involved is a very, very excellent background and activity in the field of physical modeling of the atmosphere and of the ocean. And he is coordinating, supervising all the application and development of artificial intelligence at ECMWF. So, Peter.
Thank you very much for the introduction. I hope my slides are coming up sometime soon. So what's going to happen is now Then I'm going to give you like a bit of an overview of the machine learning activities at ECMWF for like 15 minutes, and then I'm going to turn over to Fenwick, who is going to talk about the specific project that we realized together with IFAB. So I'm basically going to start talking about the bigger picture about machine learning at ECMWF, and in particular the question like why should we look into artificial intelligence and machine learning right now, and why is it different right now than it was, for example, 15 years ago? And so one of the reasons is that the data that we're dealing with on a daily basis has increased significantly over the past decades. So what you see on the figure here is the time on the x-axis over the past decades, and you see on the y-axis the sustained performance, and the different boxes that you see in the blocks are in the plot are the different supercomputers that we worked with at ECMWF. And what you will see is that in this figure, the high performance computing power has grown linearly in the plot, and it's a logarithmic plot, so it basically means that we had an exponential increase in compute power over the last couple of decades, and that's what everyone knows by Moore's law. But what's not so well known is that actually also the same is true for the archive data that we have stored, the volume of the data. So the same plot also shows you the blue line, which gives you the growth in the data that we archived at ECMWF, and it's again a linear line in a logarithmic plot, so it's an exponential law. And basically this means that we have to deal with this exponential increase of data over time, and it's kind of whatever tools are that there are that can actually help us to deal with this data volume are very beneficial, and machine learning in particular is one of the tools that's really useful to kind of extract knowledge from and information from this data, but also to deal with the data and to process it. There's also the point that there has been an enormous amount of progress in terms of hardware for machine learning. So this slide I stolen actually from Thorsten Höfler that you see on the bottom left, where he tried to collect all the different hardware companies who are building hardware specifically for machine learning and artificial intelligence. And you should see that the slide is busy, that it's a multi-billion-dollar industry. And actually the number of companies is still growing. So basically this means that supercomputing hardware that you buy today or also will be buying in the future is almost certainly going to be optimized for machine learning and artificial intelligence. So if you want to make the best out of the hardware, it's a very good idea actually to look into machine learning yourself. And then there has been a lot of progress in terms of machine learning software. So there are a couple of libraries around where you can literally build a very complex machine learning tool like a deep neural network, for example, with just a couple of 100 lines of Python code. And the software also helps you to really make a lot of progress and to make the most out of machine learning tools. And the last point is also the increase in knowledge. So we're talking about something like 100 papers per day coming out on artificial intelligence and machine learning nowadays. And this means that we are now in a much better position to really build dedicated, customized tools for your applications, and therefore kind of make much more and better use of machine learning in principle. So also, why now? Florence has already mentioned the Destination Earth project and the digital twins that we want to build. And again, we're talking about like probably hundreds of terabytes of output that needs to be processed from those digital twins every day. And their machine learning will help. And in particular, also, it could help, for example, to put in impact models and user models within our model framework to also speed up the simulations to some extent. And there are various ways how machine learning can help you within this Destination Earth project in the development of the digital twins. And also, right now, we are in the process that we call the digital revolution of Earth system sciences. And what we mean by this is that the state of the art that we basically had, let's say like 10 years ago, where we developed very large models in Fortran code and we just ported them to CPUs and we're running them and we're waiting for another processor to come around to be a bit faster, is kind of coming to a limit right now. And we now need to make sure that we are able to actually use heterogeneous hardware that is coming up right now in the modern supercomputers with our models. And this means that we have to restructure a lot of our models that we've been developing. And one of the components of this basically requires a digital revolution that we outline in this paper here. And one of those components is also machine learning. So it's also a good time in terms of the changes that we are about to do to the model anyway to incorporate machine learning into those as well. How does it look like at an institute like ECMWF? So what you see here, the boxes basically indicate what we have as a workflow in numerical weather predictions. So we collect observations, the blue box, then we perform data simulation, the green box, where we bring the observation and the model trajectory together to generate initial conditions. Then we get to the red box, the numerical weather forecasts, and then we have the orange box, which is about post-processing and dissemination of the results that we get out of our models. And if I'm now plotting all the different machine learning activities that we are looking into at ECMWF, you will be a little bit overwhelmed because there are a lot of boxes, and I'm not going to go into detail here. But what you should see is basically, it's not that there's the one machine learning application for numerical weather predictions. It's rather that there are a lot of different application areas, and those application areas are spread over the entire workflow. And also, some of them are still planned. So the blue boxes indicate projects that are just in the planning phase still. Some of them are ongoing. The green boxes indicate that those projects are ongoing already. But some of them already have been published in papers and tech memos and so on and so forth. So it's kind of really getting there. The field is also maturing in this perspective. So a lot is ongoing in principle regarding the different application areas for machine learning. There are also challenges for us. So if we want to introduce machine learning into Earth system sciences, we have to hit a couple of things. And one of them is that often the philosophy between domain scientists is different to the philosophy from data scientists or machine learning scientists. So domain scientists like to think about physical reasoning and equations. Machine learning scientists like to think about data science problems with input, output, loss function, and basically equality measurement. So often it's difficult to communicate across the different disciplines, and we need to get this going. There's also often a different set of tools from the domain scientists. For example, in our case, we have a lot of people working with Fortran and CPUs, and machine learning scientists who typically like to work with Python or Jupyter notebooks and GPUs. And also, off-the-shelf machine learning tools are often not kind of ready for our use cases, if you want. So often, like tools that we were using for image recognition, for example, are not as good if you apply them to the physical world of machine learning and Earth system sciences. We also still need to learn how to make the best use of the petascale supercomputers that we have available for our machine learning application, which is often not trivial. And we also need to understand how to introduce the machine learning tools that we are developing into the conventional workflow of numerical weather predictions. And finally, also, we need to make sure that the machine learning tools that we are developing are actually also reliable. For example, can they extrapolate into unseen weather situations that may not have been included in the training data? So there's a lot of open questions in principle. However, in the next couple of slides, I'm going to show you how we're addressing those challenges at ECMWF or also in the domain principle. So the first thing is that we should get organized. We have a lot of application areas spreading over a lot of different staff members at ECMWF and elsewhere, and also in the member states. So we need to organize ourselves a little bit. And here we have published what we call the machine learning roadmap. So we have published a document where we have 13 specific milestones that we want to reach within the next 5 years. And we also have a vision for the next 10 years, how machine learning should change our domain, and in particular also the work at ECMWF and how we interact with the member states as well. So I can only recommend, if you have a spare 20 minutes, to read this 11-page documents that you will find online. Then also we have to learn how to use machine learning at scale, how to use really the machine learning computing power that is available. And there we're looking into different projects. For example, the Milestone project, which is the Europe HPC project, where we're trying to kind of develop very customized machine learning applications for our domain. But we also built a software framework to really run those tools efficiently on modern supercomputers, and also be designing specific hardware designs for our applications. And also a big part is as well, to get into machine learning, you also need to learn from those who know how to do really machine learning in complex areas. And here, for example, we have the Center of Excellence for Weather and Climate, where we have a machine learning project where we develop together with Atos and NVIDIA. We work on a couple of projects, and some of them are addressing the challenges that I've shown you on the last slides. Then also a big point is really that we need to learn how to combine models and machine learning in one way or the other. And often the problem is, to some extent, that you can extract data from information from observations, but it's not necessarily easy to actually use this observation data for your machine learning for your conventional model application, and to actually improve your model. Fenwick is going to give you one example, but I just wanted to give you another one here in this slide. So what we've done is we looked into what we call data simulation, where you bring the observations and the model trajectory together to generate initial conditions. And here you're actually representing exactly the same weather situation at the point in time. And this means that you can actually run a very short-term forecast, like 12 hours, and you can compare the model result against the observation, and you can actually diagnose the error that you have within the model. And now you can actually try to learn the model error by the direct comparison between the model trajectory and the observation. And that's what we've done together with NVIDIA as part of the Center of Excellence. And once you've learned the model error, you can actually correct for the model error within your forecast simulation and hope that you're actually improving results because you corrected for this error that you have measured before. And these are some results. So on the left side, you see the neural network target for cross-section of for different model levels on the y-axis and time on the x-axis. And what you see there is the error pattern that we want to actually extract, given the information of the state of the atmosphere at a given point in time. And that's for temperature here. And on the right side, you see the neural network prediction, and you see that it's actually doing a good job to predict the error. So that was very, very good. We were very happy with those results. But then we also asked the questions like, how can this actually now be incorporated into our operational workflow? And now it's getting a little bit more complicated because for the plots that you've seen here, we have 12 years of data to learn the error. But in operational setting, you only have something like half a year to actually learn the new error that you would get from a new model cycle. And we repeated the exercise, and we now get the results on the bottom, on the left side, the target, and that the model error that you get for a certain modern cycle of the model. And on the right side, you see the neural network prediction, and you see that it's not kind of quite as good as the top one. So we need to learn, for example, do we also need to learn how to incorporate those tools that we develop offline also into this workflow of a model cycle that is developing over time, and so on and so forth. But there's good reasons to believe that we can get very far with this. We also built tools to make it very easy for the domain scientists to actually get going quickly. One of the tools is ClimatLab. And what we do here is that if you have a normal standard machine learning problem, you typically have a workflow that is depicted in the blue box in the middle. And you have on the top, you have a lot of code that is actually responsible for the treatment of the data in the problem. So you kind of input the data, you distribute the data over cache, you kind of bring it into a format, often NumPy in Python, to kind of be able to change the data and to work with the data. And then you have the machine learning code, and after the machine learning processing, you basically have post-processing, and you generate plots, diagnostic, and so on and so forth. And the problem is that the scientist is spending a long time in this light blue area, where they actually want to focus on the machine learning code with the dark blue area. And with ClimatLab, we hopefully go to the right plot there, where you basically reduce a boilerplate code at the beginning and at the end significantly, and the machine learning scientist should be able to really read in and change the data formats in a way that is really simple for them, and then they can focus on the machine learning code. So just before I stop and hand over to Fenwick, just two examples how we work with machine learning at ECMWF. One of them is that we want to speed up our model systems that we have in principle. And here we're looking into what we call the emulation of parameterization schemes. So what we do here is we run our forecast model, the IFS, and we store input and output pairs of parameterization schemes that are basically expensive components of the model system that represent physical features that are not representable on the given grid of the model. And then we use this data to train neural networks to actually be able to do exactly the same step as the parameterization scheme did in the first place. And then finally, we replace the parameterization scheme by the neural network within the model. Why would you do this? Because we basically can assume that our neural network is going to be much more efficient on modern day supercomputers, and it's also very much portable to heterogeneous hardware, given the libraries that I mentioned before. So it should be easy to, for example, port these model components then to GPUs. And we're not the only ones to look into this, so it's a very active area of research, but we have looked into a specific component of the parameterization scheme, which is a non-orographic gravity wave track, and we've done the emulation successfully in 2 studies. And we basically get a very nice relationship between the neural network complexity and the error that we get. We also are able to increase efficiency of the parameterization scheme by a factor of 10 when running on GPUs. And we can even actually reduce the error in comparison to the default version of the model, because our reference that we take as the truth is actually higher fidelity than the original scheme has been. So this is one way how we think machine learning is going to be make a difference by speeding up model components via the emulation. And a possible second part is also that we can use machine learning to estimate errors and uncertainties. So what I've brought you here is an exercise called downscaling. So in the first line, you have a couple of snapshots of fields of IFS over the UK, and in particular precipitation fields. And on the second line, you have the Nimrod dataset over the UK. And the IFS data has a resolution of something like 10 kilometer, and the Nimrod data has a resolution of something like 1 kilometer. And we do now a downscaling test where we basically try to map from the IFS to the higher resolution Nimrod observation data. And we do this in a collaboration with the University of Oxford. And we're using so-called generative adversarial networks. And with those, we do not only are able to do the mapping, so you can now see in line 3, 4, and 5 different realizations of this mapping procedure, but you will also see that we learn uncertainties because we can basically generate an ensemble of this mapping. So what you see in line 3, 4, and 5 are now like precipitation fields that are based on the inputs of the IFS and should mimic the Nimrod data set on the second line. And you will see that the fields look reasonable, but also the spread of the fields is kind of very realistic. So we are actually able to generate an ensemble in this mapping, and this can help to, for example, estimate the uncertainties in this mapping procedure. Okay, I think that's it from my side, and I would like to hand over to Fenwick now. Thank you.
Yeah, thank you, Peter. And yes, we can go directly to Fenwick. That will really show the project that has been supported by IFAB foundations and these the first results of this cooperation with ECMWF. Please, Fenwick.
Thank you very much, and thank you to all the previous speakers for introducing all of the different projects that are going on. I'm going to just present one example out of the many projects that are happening, and this is the example that was funded by IFAB and ECMWF. So if I could have the slides up, that would be fantastic. Yeah, brilliant. Okay, so yeah, I did a project funded by IFAB and ECMWF, like I said, applying machine learning to try and help predict 2-meter temperature and 10-meter wind. So it's a little bit specialist, but that's one part of a huge number of projects. But this work was really conducted with several people, Ziad Ben Bouleg, Matthew Chantry, Peter Duben, Peter Bechtold, and Ariana Sandu. And these collaborators actually did an enormous proportion of the work. It's not all my own work. In fact, we divided the work up pretty well between the lot of us. So yeah, there's been quite a lot of people contributing. Okay, so to get on with it and show you the basic underlying results that we got so far. This is a world map of how the error in 2-meter temperature forecasts changed with the application just of some simple machine learning algorithms to 1 year of data, so trained on 1 year of data. And each dot in this plot represents a weather station, so a station where someone goes out or a automatic machine measures the temperature and the humidity and various other things every day. And so each dot is a weather station, and the colour of each dot represents whether the weather station got better or worse with the machine learning algorithm that we used. So there was some training, and then there was some test data, and the blue dot is the result. So blue is better, and as you can see, there's huge areas of blue. So this means that the machine learning algorithms were quite well able to actually improve or predict the forecast errors to a large extent. However, there are some red dots still, especially in this plot in the East Asia. So and the odd dot in Europe as well. So this shows that it's not universally the machine learning wasn't able to universally correct all our forecasts right away. But you can also see on this plot the kind of amount that the forecast has been corrected. So a really dark blue is about 1 degree C. So that's a prediction improved by 1 degree C, and the lighter blue is maybe 0.5 degree or 3/4 of a degree. And so this is winter 2021, and it's not just winter. If you look at the plot for spring 2021, you can also see it's actually there's a higher proportion of blue across this plot. So the machine learning did extremely well at predicting that. This is summer 2021, a bit lighter, errors are a bit reduced. But autumn, we've got darker blues all over the place. There are still some red outliers, but generally the overall picture is that we've got improvement across pretty much the globe. And so let's put this result into context. So this is the current forecast error. So what I was showing you earlier was the improvement in the forecast, and this is actually what the current forecast error is for winter 2021, and you can see that the dark purple is about 4 degrees, and that can be compared with about 1 degree improvement, and the grey is about between 1 and 1.5 degrees degrees Celsius. So that's the sort of error that we're comparing against on those previous plots. Okay, so another way of looking at that is to look at the particular region. For example, if we take the ECMWF IFS weather forecast model, it's 48-hour forecast, so forecasting 2 days ahead, and its performance over Europe. And we get this plot. So we've selected Europe as the region. It's a plot that other people have produced and shown many times. And the plot, the curve at the top is the root mean squared error, so one measure of error. So we want that to go to 0, and that shows the improvement over time of the ECMWF model over the last decade or thereabouts. And the red curve is the mean error, so another measure of error, and we also want that to go to 0. And you can see that that is moving closer, ever close to 0. And the oscillations you can see are due to the season. So you can see this is the actual performance over the last decade of the ECMWF model. And we're using a slightly different data set to the one that was used to make this plot. And so just to check that our data set matched up with that, the blue dots and the red dots are for the data that we're using, just to see what the error was in that data. And you can see it's not exactly the same because it's a different data set, but we're pretty much lie close enough to the red and the blue lines, which shows that what our experiments represent this the overall model. And if we apply the machine learning algorithms that we did, then you get these black dots here. So you get a reduction in the root mean squared error, and the reduction is the reduction doesn't go all the way to 0 in the root mean squared error, but it's a substantial reduction when you look at how long it takes and how much effort it takes to reduce errors over time. And also, if you look at the red curve, the black dots corresponding on the red curve, they have also moved closer to 0. So the machine learning is able to make a reasonable improvement to these forecasts, and that's just an illustration of how big the improvement at the moment with a very quick project, what you can do. Okay, so what do we actually do? What is the machine learning that we apply? So if this is a picture of our machine, okay, it's actually it's a printing press from the Science Museum, but if that represents our machine, then one algorithm is a neural network. So we've applied a neural network to this problem. Another machine learning algorithm is the random forest. That's a particularly well-used algorithm, and that's one of the ones we use as well. And we also even apply linear regression to see how these different algorithms can post-process this data. And as an input to this machine, we can take lots of predictors or variables, like, for example, forecast temperature, forecast wind, forecast sunshine, all these kind of things, even measurements like the measured temperature or snow cover and more. And in fact, we had about 40 inputs that we could choose between, and we would pick between 10 and 25 inputs for our actual model. So we get all of these inputs coming in, and they go through the algorithm, and then after a forecast has been made, so after ECMWF IFS has provided us with a forecast, then this machinery provides a correction to that forecast. So it's just a small correction to the forecast output by ECMWF. And in addition to that, the machine learning models are able to predict the uncertainty of the forecast, so make a prediction of how certain the forecast is. So you run these machines, and what do you get? So on average, the average of the plots the average of all the stations in the previous plots is summarized here, where the horizontal axis is the forecast lead time. So that is how far you're forecasting into the distance. So it goes up to 48 hours on this plot. So if that would represent a forecasting 48 hours in advance, and the error is on the left axis. So the blue line is what we get currently, and if we apply those three algorithms, this is the error that we can reduce that blue line to. So you can see that there is a reduction, and it's a reduction at every single lead time across the across the forecast. And another thing you can see is that all of the three very different approaches actually get very similar results. And it turns out that one might be slightly better than the other, but over the course of checking on different seasons, the order of which one's best at the time kind of swaps over. But the overall message is that they all make a reduction and they all do similarly as well, and the difference between them is small in comparison with the impact they make. And in addition, interestingly, if you just take the average of all three, then you can make a further slight improvement in the model. So that's what happens, and that was the root mean squared error. This is the bias, so this is the average error, and you can see that as a forecast progresses over 2 days due to the daily cycle, the current forecast bias, which is the blue curve, you can see that oscillates about 0, which is the best, which is what we want. And the other three models, they have reduced the error towards 0 for all the different forecast lead times. And this plot is a bit of a cherry picking because it is the best of the 4 seasons, but on average, for all the 4 seasons, the bias is also reduced, as you saw in one of the earlier plots. Okay, so I also said we can predict the uncertainty in the model, but are our predictions actually any good? Are they useful? Well, the bottom plot here is called a reliability diagram, and we're plotting the predicted uncertainty against the actual forecast error. So we've done lots and lots of forecasts, and we just want to see how well whether our error was actually lined up with the error. And so on this plot, the diagonal line is the reliable answer, and that's what we want to get. And you can see that for the 3 different models, they basically lie quite close to the diagonal line. So actually our prediction of the error is not too bad. The linear regression lies slightly off the curve at the bottom, you might notice. However, if you look at the plot above, this is the number of measurements, number of forecasts that go into each of the points on the lower plot. You can see that that's between 2 and 4 degrees squared is where the majority of measurements are. And for that region, the machine learning model predictions of the error are all very good. Okay. And you get similar results for the other seasons as well. So here's an example of a single forecast station. So one station. And so the left plot is a series of 90 forecasts starting on December 2019. So each point on that plot is a single day's forecast. We're looking at the root mean squared error of that station's forecast it's a 48-hour forecast. So each point is a 48-hour forecast starting on that day. And the blue curve represents the output from the IFS model, the ECMWF forecast model, and the orange curve represents the forecast plus the correction. So you can see that sometimes the correction is quite large and does a really good job of correcting the station, and other times it does much less of a correction and it's not able to improve the forecast very much. I should say that this is a station in the Alps, and it was selected because the weather stations in the Alps are quite well improved by the machine learning. So it's kind of like a region where the machine learning does very well. And the plot on the right is a single forecast. So it starts on the 11th of December and it runs for 48 hours. So it's just one forecast. And you can see that the forecast temperature, which is the blue curve, is moving up from the middle of the night till the next morning, and then it moves. Then that forecast changes as we progress. And the orange curve is the observations. So they follow a sort of shape that the forecast is looking at, but they're not exactly the same. And the green curve is the forecast plus the machine learning correction. So that's basically that's an example of quite a good station and a forecast at that station. Okay, so what's the physical mechanisms for this? I mean, how are these machine learning models able to do this? There must be some kind of physics behind it, ultimately. So what these models have done is they've helped us find some information as to how we can improve our understanding of the physics, as in the fact that they're able to correct something means that hopefully we can find out what they're correcting. So one of the things that our models so far have been pointing to is something called the lapse rate correction. Now, I'll just try and explain that very quickly. It's a technical term, but if you imagine a model grid cell on the computer, and imagine it takes up the entire area of that photograph. So one grid cell. The real model grid cells are much smaller than that, but just for illustration. So one model grid cell, that would mean that there's one temperature at one altitude for that entire photograph. But obviously, a weather station at the top of Mount Fuji is going to give very different temperature readings, as you can see because of the snow, than temperature measurement on the plain at the bottom, which might be very warm. So the temperature measurement that you get from a weather station depends upon how high you are. So there needs to be a correction for that. And so our models are basically pointing to the fact that the lapse rate connection is not completely perfect, but can be improved. Another thing is tuning of the forecast model. So the model contains known physics, but sometimes there are some constants in that model that are unknown. And people have carefully tried to tune them and made very good educated guesses, but our results indicate that there's potentially some there's some potential for tuning these a bit further, maybe. And also there's potentially some new physics or some physics not well represented currently in the model. So we know should be there, but it's not currently there. For example, the daily cycle is shown by the machine learning models to play a very strong role. Okay, so we also looked at 10-meter wind. So that was in the title as well, but our results are not quite as blue everywhere as in the 2-meter temperature case. You can see that in over northeastern Europe, India, and Southeast Asia, and also somewhat in South America, there's some quite really dark blue areas, but everywhere else it's sort of patchy, red and blue. But due to the very blue of the regions I just mentioned, the overall error does actually go down. So this is the equivalent plot for 10-meter wind, equivalent to the plots I showed you before. So you can see that on average across all stations the error has gone down, and that's mainly due to those blue regions. But in Western Europe, for example, it's a bit patchy. Okay, so in conclusion, the error, root mean squared error in forecast of 2-meter temperature and 10-meter wind speed is reduced on average by about 15%. It's applied as a model correction after the forecast. So you run the forecast and then you can apply this correction after the forecast. The 2-meter temperature errors are reduced almost everywhere, but there are some single stations that sit as outliers. And those need to be looked into and found out precisely why that is occurring. The 10-meter wind, there's large reductions in error in some regions, so Northeast Europe, India, Southeast Asia, and South America, but there's also large regions with little or very poor impact from the machine learning. So we need either better models, more data, or maybe the IFS is already doing such a fantastic job that it's very difficult to improve on it. So there's lots more to do. So the results of this project will be fed into the development of IFS. So the way that will happen is that we're writing up a technical report, and the people who develop IFS will hopefully take note of our findings and make decisions on what to do for future forecasts. So our contribution to that will be to write the technical report to inform them. And we also can work to understand in more detail the physical mechanisms and sources of error, which if you've got a better physical understanding of the problem, you can make more informed decisions of what to improve. And also, we applied that to 1 year of data, so just 1 year. So all the variability and all the things that happen over 1 year that don't happen in a different year, we just kind of hope for the best with. But we've got 40 years of data, so we can improve and reduce our errors. So it just remains for me to say thank you very much to IFAB and ECMWF for the opportunity to do this, and my co-authors who actually completed a large amount of the work and lent their considerable experience, and all the other people who helped. So thank you very much.
Okay. Thank you, Fenwick, of your very interesting presentation. And I think that what you're doing is very useful also for the other services, because what you're doing in the old times was called post-processing, and now it's became very much more complex, and it's something that is very important to sometimes to make the forecast really useful also at local scales. So I make all my best wishes to your work, and I see that you have still a lot of work to do. And I hope that in a short time we can have a monitoring of your future progress. So I
Thank you very
I
much.
thank you, Peter. I thank you all the speaker, Florence, Sanzio, and Professor Ubertini. And I thank all the people who are connected, because for us it's very important to have the possibility to make a lot of people know what we are trying to do in this very important field. So thank you, and bye to everybody.